Welcome to the lecture on obtaining a specified precision. So, in the last lecture we discussed about the output analysis for a single system, and we have seen that when we estimate the parameter, there we have estimated about the mean. So, that was the point estimate x bar n, and then we have to, depending upon the confidence level what is given, you have to say that if the value is coming, if the value is coming from this particular mean to left and right certain quantity, then in that case we say that with that much of confidence we can say that the value will be close to that mean value. Now, the thing is that how we compute it. So, let us see that how we compute such kind of problems. So, suppose you are given for a bank, you have the, you do the different replication, different runs you are doing, and in every run you are finding the average delay in Q. So, it will be in minutes. So, you are doing 10 replications 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So, you on the 10 readings you have got the average delay values as 1.53, you have 1.66, 1.24, 2.34, 2.00, 1.69, 2.69, 2.86, 1.70 and 2.60. So, these are basically, we did 10 independent replications, and in that we got the average delay values as this. So, we have to estimate the parameter. First of all, the parameter is the mean of this average delay value, and then we have to find the obtain point estimate. So, we have to obtain point estimate and approximately 90% confidence interval for expected average delay. So, of customer. So, this way you may be told that you have to have one interval, in that if you get the value you can say 90% with 90% of confidence that this value will be under that estimate. So, as we discussed, we have to find in that the sample mean. So, sample mean will be computed as the sum of these values x I will be varying from 1 to 10. So, it will be summation of these delay values, and delay is I varying from 1 to 10 and this divided by 10. So, once we add them, after that if we divide it by 10, we are getting as 2.03. Okay. Now, we have to find the confidence interval for this value, that what should be to the what should be the half length, I mean before it, and what should be the half length after it. So, we will have a confidence interval on both the sides. So, basically what we do is, if we have got the mean, so we will have like this, and with certain confidence we are telling that this will be basically half length. So, that way we are getting this half length calculation, and for that we know that we get x bar n plus minus t n minus 1 1 minus alpha by 2, and then we are getting s square n by n. So, first of all we will find the s square n. So, s square 10, it will be summation of I equal to 1 to n and then we have the delay values. So, we will have x I minus x bar n, and then this is square upon n minus 1. So, once we do that, so every time we will do, so that will be 1.53 minus 2.03 and its square, and plus 1.66 minus 2.03 its square. So, all these will be squared and then divided by 9 because n is 10. So, once we do that, this value comes out to be 0.31. So, this value is coming out to be 0.31. Now, in the earlier case what we used the formula for finding the estimate, now that can be computed. So, we are getting that x bar 10 plus minus, then you have t n minus 1, n is 9 and 1 minus alpha by 2. So, here you have 90% confidence interval. So, 1 minus alpha is 0.9. So, alpha will be 0.1. So, 1 minus alpha by 2 will be 0.95. So, we are getting t n minus 1 and 1 minus alpha by 2, that is 0.95, and then multiplied with under root s square 10 by 10. So, that is how we are getting the result. So, we will get this will be equal to, so x bar 10 we have got 2.03 and plus minus, now t 9 and 0.95. So, that we can get from this table. Now, from this table if you look at, you have 9. So, t 9 and then you have 0.95, we are coming in this side. So, it is coming out to be 1.833. So, if you look at this, it will be coming as 1.833. So, it will be 1.833 under root s square n is coming as 0.31 divided by 10. So, if we get these values, it will be basically 2.03 and plus minus 0.32. So, we are getting interval of 1.71 and 2.35 minutes. This is the interval which we get, and we say that with 90% confidence that the value will be in this interval. Now, the thing is that here you are having the mean value, sample mean is 2.03 and we are having the half length of 0.32. So, certainly this is the half length. So, this much it has to vary either to the left or to the right. Now, the thing is that in many cases it may go very high. So, if the number of replication n is small, then the confidence intervals might be too wide. Now, that can be seen by looking at the table, that if the n is smaller, then you see for any value, this value goes on increasing as we move up in the table. So, if that basically will go on increasing, in that case the half length will go on increasing. So, this interval will go on increasing if the n is small. As n will be larger, it will be going on smaller and smaller. So, the thing is that is not basically going to be useful. So, what happens that in many situations we are specifying that what should be this half length. We are basically specifying the precision. We say that you tell me, now the thing is that to decrease this half length we have certain options. We have some options how to decrease this half length. Now, if you look at this expression, the expression of x bar n plus minus t n minus 1 1 minus alpha and under root s square n by n. In that case you have three ways. One is that if we increase the alpha. So, if we increase the alpha, the this half length, half width will be reducing, but then increasing alpha means this probability value is increasing. In that case the chances of the number going beyond that will be more. So, that is not basically advisable. Now, we can decrease the s square n. So, that also basically we can do, but then we have to take it as a fixed one, normally that is a fixed quantity. So, then the last option is to increase the value of n. Now, if we increase the n value continuously and if we keep the s square n value fixed, in that case, so we have the expression is like x bar n plus minus t n minus 1 1 minus alpha by 2 under root s square n upon n. So, in this case now this is the half length, and what we see, if we have seen this problem, we see that it is approximately about 15 to 16% of this x bar 10 value. So, we see that this 32.32 is something close to 15 to 16%, and in many cases it may go quite as high as 40%. So, basically that is not desirable. So, in many cases what we say that we will specify this, that it should be how much, it should be what percent, it should be what value. Suppose we say that it should not be more than 0.2 or more than 0.15. So, in that case, as we discuss the different cases, now we have either we can increase alpha, either we can decrease this s square 10. So, that is basically kept fixed in most of the cases. Then we have, so as we discussed that we cannot increase alpha, because that will giving us more chance that the estimation will be outside that limit, it may go. So, because it will be coming quite narrow, and then we can increase this n. So, we can increase this n. So, as we increase n for a fixed s square n, in those cases we can see that we have this lesser value of the half length. So, that is what is known as obtaining the specified precision. So, increase n until half width is small enough. So, we have to increase this value of n, and iteratively we have to go, and we have to see that when this half length will be coming to a certain value. So, for again we will see that how it can be done, and then we can solve through a problem. So, what we see here is that in this case you have x minus mu p. So, in that we have the probability value x minus mu is less than equal to beta. So, this beta is nothing but this value is x bar minus mu, that value should be basically beta, and this is specified, it should be less than equal to beta. So, this probability value is basically equal to 1 minus alpha. So, we are telling, so we will get the expression that, or we will have the question like you go for that many number of replications, so that you are getting that specified precision. So, ultimately you are going to have the number of runs, that is for specified beta, and it should be minimum of that run where I will be more than equal to n. You have already run for I, after that how long you should run, so that the half length reduces to that particular value. So, for that t I minus 1 1 minus alpha by 2 under root s square n by n I, it should be less than equal to beta. So, basically we are every time changing the n or I, and then we are seeing that when this value will come to that particular value. Now, let us see that we have the problem again. We are told that in this case we need to have the half length lesser than certain specified value. Now, suppose we got here this half length has 0.32 and we need to get it to 0.25. We want to reduce this 0.32 half length to 0.25. So, for that we have to increase the n. So, I will be increasing, and for every increase we have to then. So, basically in that case this parameter will be changing. So, we have got for 10, if you go to 11 this parameter will be t 10 and 1 minus alpha by 2, and then this will be again s square n is already fixed. So, it will be by 11. So, similarly for 12, 13, 14 and 15, 16 or so. So, we have to go till we get this result. So, suppose for the same bank model, if we are to find, we like to estimate expected average delay with absolute error of 0.25 minutes and confidence level is 90%. So, what we had seen in the earlier case, we had the values and based on that we found the sample mean, and then we found the confidence interval for the 90% confidence level. Now, in that we want to check the half length. So, that is error basically, that is why it is error. So, half length both on the left and right side. So, that is basically known as the absolute error. Now, that is to be basically confined to 0.25. So, 0.25 minutes, in the earlier case it was 0.31 or so. So, in that case what will happen? You have to find for some value of number of replications, and where you have to get the value of 0.25, it will be minimum of the number of replications where it will be more than 10. Already we have started from 10. So, after that you have to go, because at 10 you are seeing that you have that absolute error close to 0.3 or so, but you have to come it down, bring it down to 0.25. Now, for that the value, once we change the I will be, so it will be I minus 1, 1 minus alpha by 2, and 1 minus alpha by 2 for 90% it will be basically 0.95. So, you have to write it as 0.95, and then you have under root s square n by n. So, s square n we are taking at fixed. So, it is 0.31, and then this will be changing, that is I. Now, that should be less than equal to 0.25. So, after 10 you have to check it. Now, suppose after 10 you have to see for every I you have to check it. So, supposedly you take I equal to 15, I equal to 15 suppose you are taking. So, what will happen at I equal to 15, this value will be t. So, this t I minus 1, 1 minus alpha by 2 under root s square n by n, that will be basically equal to t. This is 15. So, this will be 14.95 under root s square n by n. So, that is 0.31 by 15. So, t 14 0.95 we have to look from the table. Now, if you look at the table, in that T14 and 0.95. So, it is coming out to be 1.761. So, it will be 1.761. So, it will be 1.761 and into under root 0.31 by 15. So, it is coming out to be 0.253. So, if you go to 16, it will be lesser. If you go to 16, then suppose you go to, so further, so certainly it is bound to, so it is just coming to 0.253. So, it will be coming to, so it is not still coming 0.25, it is 0.253. So, if you go to 16, it will be done just below that. We can compute I equal to 16 and you will get some values at 16 which will be just below 0.25. So, you can say that if you go for n equal to 16, so that much run you have to complete, and so that you must have that many numbers, so that you have the specified precision of 0.25 is achieved. Now, so what we see is that either you can specify a particular value of beta, that is beta is greater than 0. So, for that you are going for big enough value of n, so that the half length is less than beta. Many a times we are also given the relative precision, that this precision what we get, that error there in the relative terms this value is given, like this value divided by x bar n, that fraction is specified. So, many a times either you have absolute value given or you have the relative precision given. So, what do you mean by that relative precision? So, in that case x bar minus mu divided by x bar, so that value is given in terms of certain decimal. So, basically what we say is that x bar minus mu and divided by basically x bar. So, that basically we tell it as a value that is specified. So, this is the relative precision. So, in those cases we can say that this means that this x bar has a relative error of nu. Now, what do you mean by that? So, basically either it is expressed in terms of a particular absolute value, or we also tell it in the terms of relative error value. This is said to be the x bar has a relative error of gamma. Basically it is with respect to this mu. So, we will have mu here, because x bar how much it is this deviation, how much it is deviating from that actual mu, and what is the relative difference. So, that is how the x bar minus mu, that is defined as the gamma, and in that case you have the expression further, and in those cases what we get is that we are getting the, so for getting certain that relative value we have the expression. So, for a particular relative error of value gamma will be equal to minimum I is more than equal to n. So, because it is relative error of y with respect to mu. So, and we have to see with respect to x bar. So, in case of x bar it becomes gamma by 1 plus gamma. So, that is why the expression comes like this: T I minus 1 minus alpha by 2 under root s square n by I, and again by you have x bar n. So, this will be less than equal to gamma dash. So, because we are relatively looking with respect to, so we know x bar n. So, accordingly we can see with relative sum of the arithmetic operations, this gamma prime comes, out to be gamma by 1 plus gamma. So, this gamma prime is coming as gamma by 1 plus gamma. So, if it is 10%, suppose we get 10% of relative error. So, if the gamma is 0.1, in that case 0.1 by 1 plus 0.1. So, it will be something close to 0.9. So, for 0.9 we have to get these values. Now, if suppose we have the same condition in case of the earlier problem which we discussed, and we are given that we like to, so if you like to estimate expected average delay with relative error of 10%, and confidence level of 90%. So, what will happen? You have to go for n more than 10, so that this relative error comes out to be only 10%. So, in that case what we see is NR. So, we have to go for 0.1, we have only 10% is specified, and for that we are going to see for all the values. So, we will go on increasing that. So, I will be more than equal to 10, and for that t I minus 1 and then 1 minus alpha by 2 again. So, if the 1 minus alpha is 0.9, so 1 minus alpha by 2 will be 0.95. So, it will be 0.95, and then further s square I by I. So, it will be 0.3 by I, and then divided by x bar. So, x bar I will be something 2.03. So, x bar 10 we know that. So, that is 2.03, and that has to be less than 0.1 by 1 plus 0.1. So, we are going to do it, we are going to iterate this process continuously, and if we do that we are getting this NR. So, for certain relative error value we are going to get it when we will going to 27. So, what we see that when we do the less number of replications, as we have seen that we tried initially for 10 number of replications, n was 10. For that, with the mean value, sample mean value of about 2.01, you had the half length coming out to be 0.32. Then we were told that we have to decrease this half length. So, half length was basically decreased to 0.25, because many a times you say that you go for large number of replications, so that you can say with that much confidence that the half length is reduced, the area that is basically. So, as you go on increasing the number of n, this half length will be going on reducing. So, we saw that when the n was increased to 25, I mean n was initially increased to 16. So, at 15 we checked, and at 15 it was just coming to 0.253. So, when that was specified as 0.25, then we assumed that at 16 number of iterations we can come to that value of 0.25, and then relative precision was also set. So, we were told that you have to have the relative error of 10% maximum. So, in those cases you have again to increase. So, in that case once you increase this n to 27, as we see that once you increase this number of runs to 27, in that case you are getting this condition fulfilled, that you have relative error of only 10%. So, many a times when we do the simulation, we are said that the relative error should not be more than this, and you have to run for that much of time, or how much should be the n, what should be the number of values of this n, so that you get a particular value of this relative error. So, this is for the analysis of different type of such situations. Now, apart from that, we have already studied that you have steady state behavior also. So, this was for the terminating type of simulations, and when we have non terminating type of simulations also. And now, in that case when we discuss with the steady state type of behavior, in those cases you have some way, basically you are specifying the initial conditions initially, that for what conditions up to what time basically you have to neglect or you have to delete the values. So, in those cases you have to come to that condition, and then you have to take the data and then further you have to analyze. So, that happens in the case of the steady state analysis, and then the same process applies. Once you have the mean values, you find again the half length, and from there you can estimate the different parameters. Thank you very much.